Bismillahirrahmanirrahim. Dear students, this is the position paper Bio-Nanotechnology, and this is second lecture of Bio-Nanotechnology. Bio-Nanotechnology, whose course code is CHEM4141, and in this lecture we will talk about effect of length scale on properties. The key concepts about which we will talk, they are a little introduction about nanoparticles. We have already introduced nanoparticles in previous lecture, but again I will recall for you something, and I will give some introduction about nanoparticles. Then the second thing we will discuss about size dependent effect. What is size dependent effect? Because we are talking about effect of length scale on properties of nanoparticles, so we will talk about size dependent effect. The third one is the surface to volume ratio. How to calculate surface to volume ratio? First of all, how to calculate the surface area of the nanoparticles, and then we will compare surface to volume ratio of nanoparticles to the bulk materials. And on last, we will talk about effect on properties of nanoparticles, the effect of a small size of nanoparticles on their properties. The term nano is derived from the Greek word nanos, which is used for dwarf. This etymology and its placement on the metric scale shows that tiny dimensions which are not visible to naked eye beyond the normal limits of our observation. So these kind of entities, they are nano entities. The diameter, simply I am just recalling for you, the diameter of simple hair is 100 micrometer, and if we compare the hair with fullerene, which is Buckminster fullerene, it is a carbon-16 compound, its diameter is only 1 nanometer. So this is the variation in the diameter. Nanoscale materials are defined as materials having at least one dimension in 10 to 100 nanometer range, in which nanoparticles are the major investigated subjects. And the term nanoparticle was first appeared in 1980s. And this is the same picture which I have mentioned in the previous lecture, so I will not repeat it again. Now, the synthesis of nanoparticles of different size and shape has received largest activity in the past few years as a result of their peculiar and fascinating properties and their applications superior to the bulk counterparts. The most successful example is the microelectronics, where smaller has meant greater performance ever since the invention of integrated circuits, which leads to more components per chip, faster operation, low cost, and less power consumption. This is a best example of nanomaterials where the nanoparticles shows highest activity. Now the question is, how smaller has greater performance? It means how a smaller particles can have greater performance. This is the question, and we will try to answer this question. It has been observed that in earlier times the bulk materials were characterized by the properties such as the people were trying to find their composition, their solubility, melting point. Melting point is little bit about their physical property, and boiling point, vapor pressure, pH. So these are the earlier studies about bulk materials. But as the size decreased, the criteria for the characterization for the nanoparticles also changed. When the nanoparticles were discovered after that, they were characterized by their size, their shape of interfacting surface, it's very important, their shape, then melting point, and surface area is also very important, wettability, surface tension, band gap, and pore size. Sometimes nanoparticles can have little small pores, smaller than nano size. So these properties were used for the characterization of the nanoparticles. Now, what happens when the nanoparticles are grown or when the bulk materials are converted into nano size? What happens? This is the question. There are basically two types of size dependent effects. One is the surface effect and second is quantum confinement effect. So these two effects are the reasons for which the nanoparticles show peculiar and very enhanced properties as compared to bulk materials. The dispersion F of a sample is defined as the fraction of percentage of atom at a surface relative to the total number of atoms in the sample. Dispersion F is equal to surface area to volume, and surface area is calculated by 4 pi r square, and volume, when we divide 4 pi r cube over 3, it becomes volume. Dispersion is A over V. In other words, if we take A and divide by V, then we get 3 over R. If we combine these two equations, this one and this one, then F becomes A over V, 3 over R, or 6 over D. R is the radius and D is the diameter. If the diameter of a specimen reaches to the diameter of two atoms, every atom is directly exposed to the surface and F becomes 1. In other words, if the diameter of a specimen reaches to the diameter of two atoms, here if we write 2, then every atom is directly exposed to the surface and F becomes equal to 1. So this is the surface effect, that when materials go to nano size, their surface area increases. Here it is the picture for dispersion. This figure shows the EG of a cubic crystal with n atoms along an edge, and total number of n is equal to n cube atoms, where n is number of atoms in the cluster. The smallest cube has 8 atoms and each of them are at the surface. You can see this is the smallest, this is the biggest. In smallest particle there are 8 atoms and each atom is striking with the outer atmosphere, with the air. On the other hand, if we see this picture, there are some atoms here which are inside behind these 3 atoms, and in this picture there are more atoms. So as the size increases, the exposed atoms becomes lesser and lesser. As you can see here, these are the exposed atoms, but if we go towards the back side, the exposed atoms quantity decreases as we move towards the back side. So this is the size effect. You can say the surface area decreases if the size increases, and if the size decreases, the surface area increases. So it is very good example to show the size effect. Quantum confinement effect in materials with delocalized electrons. Atoms have three well-known atomic orbitals. The core of the orbitals are confined to relatively small volume and remain localized. Each of the n atoms contribute uh, with its atomic state to a band so that although the width of the band increases slightly, when more atoms is added, the density of the state within the band is basically proportional to the number of atoms with an ensemble with extended band structure. Thus, the density of state is very large for a bulk amount of matter but low for a small cluster. So this is the second effect, quantum confinement effect. Here we can see this is macroscopic, this is mesoscopic, and this is microscopic. And this is bulk material where the density of states increases, and in small molecules the density of states they are decreasing. Besides small size, again here we will explain the surface area, how to calculate the surface area, and we will try to explain surface area to volume ratio. Besides the small size, the characteristic feature of nanomaterial is that their vast surface area is very important. This concept can be illustrated by this figure. Just take a cube with edges 1 centimeter in length and divide the cubes with edges to 1 nanometer in length. First of all, look at this cube. Its length is 1 centimeter. Its height is also 1 centimeter and width is also 1 centimeter. We know that 1 centimeter is equal to 10 millimeter. So this one cube, one small piece from all of this, it is 1 millimeter in size. We can say this big one can be divided into 10 cubes of 1 millimeter of each of them has length, width, and similarly towards the back side and towards the upper side, this cube can be divided into 10. So one cube of 1 centimeter cube, it can be divided to 10 cubes along x-axis, 10 along y-axis, and 10 along z-axis. In other words, 10 raised to power 3 times 1000 cubes can be made from 1 centimeter cube, and we can get 1000 cubes of 1 millimeter. Now if we take 1 cube of 1 millimeter and we divide it further into, we know that centimeter can be divided into millimeter, millimeter can be divided into micrometer, micrometer can be divided into nanometers. So we need to divide this cube 1 lakh times. First it will be divided into 10, again 10, again 10, 10 multiplied by 10 multiplied by 10, and finally we will get 1 cube of 10 nanometer size, and out of which only the small cube has 1 nanometer size. This is the table which shows the calculations from previous figure. If we divide 1 centimeter cube to 10 nanometer, 1 nanometer cubes, then how the surface area, how much can increase. All of the cubes, their overall volume is 1 cubic centimeter. The first one, whose edge length is 1 centimeter, it has only one number of cube and its volume is this one. Its surface area is 6 centimeter square. How we can get 6 centimeter square? It has 6 sides and each side has 1 centimeter square surface area. So 6 sides, 6 multiplied by 1, so 6 centimeter square surface area. If we distribute 1 cube into millimeter size cube, 1 centimeter cube to millimeter size cube, we get 10 raised to power 3 number of cubes. Overall volume is 1 centimeters cube, but the surface area will increase. How much it will increase? 60 centimeters square. It means we need to multiply 6 with 100. Why 100? Because 1 centimeter is distributed to 1 millimeter. We need to distribute 10 times, and for surface area there is the power 2, so 10 multiplied by 10, 100. So 6 multiplied by 100, it becomes 6 multiplied by 10, it becomes 60, because each 1 centimeter cube can be dissociated to 1 millimeter cubes 10 times. So we just multiply with 10. 6 multiplied by 10, 60. Similarly, when we reaches to millimeter to micrometer, the number of cubes become 10 raised to power 12. Overall volume remains the same, but the surface area increases. It becomes 60,000. So we need to multiply 6 with 10 raised to power 4. For 1 nanometer, we need to multiply 6 with 1, 2, 3, 4, 5, 6, 7, 10 raised to power 7, because we know that 1 centimeter is equal to 10 raised to power 7 nanometer. So the surface area becomes more than 6 lakh, about 1, 2, 3, 4, 5, 6 and 7. It is 600,000. The surface area of 10 raised to power 21 nanocubes, which becomes 6,000 meters square. It is almost the surface area of football field, which is calculated 7,000 meters square. It is just created from a single cube of 1 centimeter. Now you can imagine that if we decrease the size of one cube of 1 centimeter, if we divide 1 centimeter cube into several cubes of nanometer size, then how the surface area can change. Hence the surface area of material bulk increases dramatically when the particle size decreases to nanometer range. This is actually the surface to volume ratio, and it is very amazing property. Next is effect of surface area, effect of small size on the properties, which is actually the topic we are trying to discuss. The interest in nanoscale materials is due to the fact that new properties are acquired at this length scale, and equally important that these properties change with their size or shape. The change in the properties of a material at this length scale when compared with the bulk material results from different causes in different materials. So the change in the size from bulk to nanomaterial. Different materials exhibit different kind of effects, or different effects or different causes occur in different materials and change their properties. We will discuss some examples and some common properties which are changed by decreasing the size of a bulk material to nanomaterial. A good example of the effect of length scale on properties is the study of catalysis. We all know that what the catalysts do. They just take part in a reaction, and they are being used. After the reaction, they are being recovered. Just they increase the rate of the reaction. They provide a place, a platform for the reactants to combine with each other. So the reactants just attach with the catalyst, and their activation energies are enhanced. They are easily activated. Their activation energies are decreased, not enhanced, decreased, and they are easily activated. And after that, they detach from the catalyst. No, If the catalyst has more surface area, it has more place for the attachment of the reactants, then the reactants will be converted to products more easily. So the first one, while discussing about the effect on properties, we will discuss effect on catalytic properties. These nanomaterials can be used as catalyst itself or as a catalyst support. Nanoparticles find an important application in heterogeneous catalysis. As the catalytic reaction occurs on the surface, the available catalyst surface area correlates directly with the turnover number of material. And in case of noble metals, we know that noble metals are very expensive and it is very difficult to use them as catalyst. This is why we mostly use transition metals instead of noble metals. So in case of noble metals, if we use nano-sized noble metals, then we need to use a small quantity of noble metals. Small nano noble metals will be enough for a reaction, and this will be cost effective. The heterogeneous catalysis is another example of a major industrial relevance for nanoparticles. The heterogeneous catalysis is an example of major industrial relevance of nanoparticles. This is another example. Next one are the electronic properties. Different materials can be classified into three classes as metals, semiconductors, and insulators depending upon their electronic. This classification is based on differences between the valence band and conduction band. It is shown in figure 1.3 on the next page. Valence band is the lower band and the conduction band is the upper band. Electrons move from valence band to conduction band. Semiconductor nanoparticles find applications in nanoelectronics, optoelectronics, photonics as a sensors, medical diagnostics, catalysis and photocatalysis. The semiconductors are mostly grown in nano size, in nano scale size. So this is why they have plenty of applications in different fields. In most of their potential applications, quality and structure of the surface plays a pivotal role in determining their functions. And now I will show you the figure 1.3. The first one is the conductor, where there is no gap between the valence band and the conduction band. This gray area is valence band and this empty area, it is conduction band. However, in semiconductors we can see there is small gap between valence band area and conduction band area. And in insulators there is a large gap. This is why insulators are insulator, because the electrons cannot move from valence band to conduction band. In conductors, electrons can easily move from valence band to conduction band, and in semiconductors they less easily they can move. So these are three different types of materials. Conductors are also called metals, semiconductors are also called semi-metals, and insulators are non-metals. Sometimes we use this word. For conductors we can use the word metals. Number 3 are the optical properties. Optical properties are also very much concerned with the surface of the materials. The physical and chemical properties of nanomaterials depend not only on their composition but also on the particle size and shape. So optical properties are also somehow physical properties. According to a high quality synthesis protocol must first of all provide control over particle size and shape. For example, if the diameter of gold nanosphere is made to increase, the surface plasma resonance will be gradually shifted from 530 nanometer to longer wavelength sides. Again, if the diameter of gold nanosphere is made to increase, if the diameter of nanosphere, which nanosphere of gold nanosphere is increased, the surface plasma resonance will be shifted from 530 nanometer to longer wavelength. Thus, if nanoparticles differ in size, their optical characteristics will also change significantly. And this is figure 1.4. Surface, I just mentioned in previous slide, surface plasma resonance. It is actually a kind of spectrophotometry. Just like UV visible spectrophotometry, it is UV visible spectra. And in this spectra, at the bottom you can see wavelength from 400 to 700 nanometer, and on y-axis you can see the absorbance of the material. If you have already studied Beer-Lambert law and you know about lambda max means the wavelength at which a material absorbs maximum of the radiations. For example, here this is the lambda max at this wavelength. This is about 530 nanometer. 530 nanometer. This is for a gold nanosphere of diameter 9 nanometer. Its diameter is 9. You can see from 9, then the diameter increases to 22, then 48, and then 99. This lambda max is shifted from 530 towards longer wavelength, towards this side. It means when the particle size increases, it is more preferably it absorbs the wavelengths of the radiations of higher wavelengths. So this is the change in the optical properties. When the materials are of smaller size, it is not very necessary that all of the materials will absorb radiations like this, but in some cases there will be variation in the absorption of radiation. Next are the magnetic properties of nanoparticles. Magnetic properties of nanoparticles also depend upon the size of the nanoparticles. As an example, the magnetization curves, which are also called hysteresis loops, or it is called coercivity and remanence. These are shown in this figure. These hysteresis loops are taken for cobalt at the temperature of 5 Kelvin, and here is the applied field on the x-axis, and on y-axis it is magnetization. In hysteresis loops, if magnetic field is applied, then the magnetization increases as the applied magnetic field value increases, and it goes from negative to positive, and it goes from negative to positive. The magnetization also goes from negative to positive. So after coming back during the hysteresis loop measurement, when we go back from a higher applied field to lower applied field, the hysteresis loops persist. They do not change abruptly. So this is hysteresis. So here we can see with the decrease in particle size, the hysteresis loop becomes smaller. For example, for 11 nanometer particles, this is the blue one, and for 8 nanometer, the red one, it is smaller than from as compared to 11 nanometer size particles, and the 6 nanometer particles show more smaller hysteresis loop, and similarly the 3 nanometer particles they show more or less hysteresis loops. The loop is more smaller. It is not necessary that always the hysteresis loops decreases, they may increase. Next one is the melting point. It is a general physical property, and melting point is measured by using melting point apparatus for certain particles. It has been observed that as the particle size decreases, the melting point decreases. It is because the surface energy increases with increase in surface area. We have already discussed earlier that when we go to nanoscale, we get very high surface area to volume ratio. The nanoparticles, they have very high surface area, and we have also discussed that when we go to nanoparticle size, the nanoparticles have their surfaces more exposed to the external environment. Just on previous slides where we have 1 cube of 8 atoms and 1 cube of several atoms, we have discussed that 1 cube of 8 atoms, all of the atoms are exposed to the internal environment. And similarly, here when we want, if we want to melt some solid material, and if the solid material is in very small size, then what will happen? The all of the surfaces, they are exposed to the external environment. So this is why the heating energy which we provide to melt the substance will be efficiently provided to the material, and the material will melt at very low temperature. A very small amount of energy will be required to melt the solid material. Here it is a melting point curve. On the x-axis they are particle radius in nanometer from 0 to 11 nanometer, and on y-axis it is melting point in degree Celsius. It is the curve for the gold nanoparticles, and it is very surprising that when the gold nanoparticles are of the size of 11 nanometers, then the melting temperature, this is melting temperature, it is 1064 degrees Celsius. As the particle size decreases from 11 to 10, the melting point also decreases. Again, the particle size decreases, the melting point decreases, and it continues until if we get 1 nanometer or 2 nanometer size gold nanoparticles, and we can see the melting point already reached to about 500 degrees Celsius, and it is very smaller. These dots are representing the melting point values, and this line curve, it is just drawn by the software. It does not mean the melting point can reach to zero. It is an approximation, but actually the values are the dots which are shown here, this one and this one and this one. So this is an example of melting point. As the particle size decreases, the melting point decreases, and it is very good example of gold nanoparticles where the melting point starts to decreasing from 1064 degrees Celsius, and it reaches to 500 degrees Celsius. And it is very good property that we almost need half of the temperature to melt gold nanoparticles when their size is very small. Next is the reactivity. We have already discussed the electronic structure of nanoparticles, which depends upon their size. The electronic structure of nanostructured materials depends on their size, their ability to react with other species, and also depends on the size of the particles. This has important application for design of catalytic agent. As with decrease in size, the surface area increases, so nanostructure have more surface area for reaction. It is very similar to the catalysis where we have discussed that as the size decreases, the material will have more surface which is exposed to the other reactants. So similarly, when we talk about the reactivity, and in reactivity, when two reactants they react with each other and they form a product, it is very simple practice that both of them they will collide with each other, their surfaces will react with each other, and those materials which have their surfaces more exposed to the external environment, they will react more efficiently. So we can say that the reactivity increases with decrease in particle size. When we synthesize different kind of materials, either we use solid state or we use some wet chemistry technique. We know that, if, for example, if we use a wet state chemistry, we need to dissolve certain kind of solid materials into the liquids, and when we dissolve, they get dissolved. They will be more near to each other, and they will react with each other. But even if their particle size is greater, then it will be difficult for them to react with each other, because as the surface of one particle collides with the surface of the other particle, so as the surfaces of the reactants, they interact with each other, they are converted into the product. So this is very good example of the nanoparticle size effect on the properties, that their reactivity increases with decrease in the size of the materials. Another very good example of nanoparticle application where the size affects the properties is the sunction lotion. Sunction lotion has been used as protection against ultraviolet radiations that has been commercially significant for quite a long time. The sunlight contains different kind of radiations. It also contains ultraviolet radiations which comes to our earth, and it affects our skin, and sometimes we have protection. We need to protect ourselves from ultraviolet radiations. UV visible light does not affect our body, and ultraviolet radiations, they come from the sunlight because of the depletion of ozone, and there is possibility that ultraviolet radiations, they can come towards the earth. The sunction lotion contains titanium oxide and zinc oxide nanoparticles whose diameter is 30 to 80 nanometer, and they can serve as a simple example of the optical transparency of thin layers of nanoparticles. When the size of nanoparticle is well below the wavelength of visible light is 380 to 780 nanometer, and the size of the nanoparticle is 30 to 80 nanometer. So it can stop the coming radiations, and it can stop this wavelength. And also the ultraviolet radiations, they can also be stopped by this size of nanoparticles, 30 to 80 nanometer. So while a thick layer, what we do, how to use the sunction lotion? While a thick layer of sunction lotion appears milky white because of diffuse multiple scattering at the nanoparticles, a thin layer on the skin is transparent, which is no longer visible to the human eye. So if we use a very thin layer of sunction lotion on our face or on our skin, it is transparent and it cannot be observed by visible human eye. So this is why we can use a very thin transparent layer of sunction lotion, which is milky white when it is thick layer, but it becomes transparent when it is thin layer. And we use this thin layer, just we apply this layer on our skin, and it is invisible, no one can see, but it will protect us from sunlight and ultraviolet radiations. So this is all about this lecture, effect of length scale on properties. I can recall whole of the lecture by going to each slide one by one. So starting from introduction, we have introduced the nanoparticles. Nanoparticles are the particles which are in the range of their size is 10 to 100 nanometer. It may be less than 10, but normally we say 10 to 100 nanometer. And then this is the figure 1.1, which shows comparison of nanoparticle with human hair. Then we talk about something when the particle size gets smaller, its performance increases, and we need to explain how the performance increases. And also we have discussed that bulk materials were characterized by these six properties: composition, solubility, melting point, boiling point, vapor pressure, pH. But as the size decreases, the criteria for characterizing has been changed. It was changed to size, shape of interacting surface, then melting point, surface area, wettability, surface tension, band gap, and pore size. Then we have discussed about size dependent effect. There are two effects due to the size. One is the surface effect and the second one is quantum confinement effect. And the surface effect says that as the particle size decreases, the surface area increases, and surface area to volume ratio also increases, while the quantum confinement effect says that there are delocalized electrons, and when we have smaller molecules, then the delocalized electrons will be lesser. So this is why the density of states will be smaller. So this is the other picture of the size effect on the nanoparticles. Then we have discussed surface to volume ratio, and we have taken an example of a cube, and when it has been distributed into 10 or 1 nanometer cube size, then the surface area increases to dramatically to a large value, about 6000 meter square, which is only 0.00006 meter square when the cube is of 1 centimeter and it has not been divided into 1 nanometer cubes. So this surface area, it is very big surface area as compared to a football field. Almost it is the surface area of a football field. Then we have discussed about the properties which are affected by the particle size. The first example we have discussed is the catalysis, and we say that as the particle size decreases, the catalytic properties increases because the surface exposed to the outer environment increases, and it gets easy for the reactants to get attached to the reactants and to get converted into the products. Then electronic properties, it has been observed that semiconductors materials are of three kinds: metals, semiconductors, and insulators, and it has been observed that semiconductor nanoparticles find applications in different fields like nanoelectronics, optoelectronics, photonics, sensors, medical diagnostics, and others. Then this is the picture for metal, semi-metal, and insulator. Metal is also called conductor, and semi-metal also called semiconductor and insulator. There is band gap between conduction band and valence band, which makes them different from each other. Then we discussed about optical properties, and we say as the surface area decreases, the wavelength absorbed becomes lesser in size, lower wavelength, and as the particle size increases, the particle absorbs higher wavelength radiations. Then about magnetic properties, we have discussed hysteresis loop of a certain kind of material where as the particle size increases, the hysteresis loop decreases. It has been observed. And very good example of effect of size on properties is the melting point. We have discussed about melting point of gold. It is 1046 degrees Celsius and it decreases to 500 when we move from 11 nanometer to about 2 nanometer of the particle size. Then reactivity, it is very common thing that reactants react with each other and their surfaces interact with each other. So if the surface of the nanoparticle is small, then it will, if the nanoparticle is small, its surface will be more exposed towards the other things. So the reactivity will increases. And sunction lotion, it is a protective coating. It is transparent when it is very thin and it is invisible to human eye. So this is why we can apply this sunction lotion on our skin and it will protect us from ultraviolet or visible light whose wavelength is larger as compared to the diameter of the sunction lotion nanoparticles, which is about 30 to 80 nanometer. The references for the this lecture are one of them is there is plenty of room at the bottom. The player of finding things out. This is the lecture Nobel laureate Richard Feynman, and the second one is Introduction to Nanoparticle by Satoshi Horikoshi and Nick Serpon. These are two authors from I think Japanese. They are Japanese, and the students may ask me for these books if they don't find from internet. The references are students have to draw diagrams showing different type of nanoparticles depending upon their morphology and size. I think it is similar to the previous assignment, which was just for overview of the nanoparticles. The students have to search and summarize three more properties of nanoparticles that depend upon the size of nanoparticles. Yes, this is very important because I have just discussed few properties like electronic, magnetic, optical. Students can find more properties, and the references for this lecture, they are two PDF files. If students want, I can mail them for further guideline. This is all about this lecture. Thank you very much. Allah Hafiz.